So now let me just run the application. Now let's take the trace. So I have just opened the system software, and let me just go to my IDE, reset it, and just run. And now do the UART configuration, and let's start recording. Here it is. We are actually getting the trace. Now let me hit the button a couple of times. Let me hit the button 3 times. Now you see all tasks got deleted. So now we are not seeing any printf messages. So let me pause it. And now let's analyze this trace. First of all, you see now there is one extra tab has appeared, ISR22. That signifies the execution of an interrupt handler. That is our button interrupt handler. It actually signifies the IRQ number or the exception number of the exception. It is showing 22. If you go to your application in the main.c, you see there is one function called GPIO in it, which configures the GPIO. And in this function at the end, you see NVIC enable IRQ with this IRQ number. So this IRQ number is the IRQ number of the EXTI0 interrupt, and which happens to be 6. So you have to add the offset 16 to this because that signifies ARM Cortex processor's exception numbers. That's why add offset 16 to this. That's 22. So that's what it is showing here. The exception which was triggered is exception number 22. That's what it signifies with exception number 22 has triggered. Now let's see where exactly we received the first button interrupt. Just use this left arrow, and here it is. This is a place where we received the first button interrupt. Let's analyze that. Right, here it is. This was our first button interrupt. So the button interrupt handler ran for 13.5 microseconds. And this is a place where it notified the task. You see here, it calls X task to notify is equal to LED green. So it notified to the LED green. And what happened afterwards? You see here, this is actually the exit of the ISR, and it exited to idle task. That's interesting. Here at this place, what happens? The higher priority task, which is nothing but LED green task, wakes up, isn't it? Because it received the notification. Here, the higher priority task, which is LED green, wakes up. Strictly speaking, the ISR must exit and it should resume a higher priority task which just appeared in the ready state. But it is not doing that. What's happening here? When the ISR exits, it is returning to the idle task just got lower priority. Basically what's happening here, so idle task was running, interrupt came. This is the execution of interrupt context. So interrupt handler ran, and this was the exit of the interrupt handler, and the task which was interrupted just resumed here. But strictly speaking, so the ISR should exit and the control must return to that task which just appeared into the ready state, that is LED green. So the reason for this is not using this field in the X task notify from ISR. After that, what happens? Let's trace further. So idle task continue to run here, and here comes the SysTick interrupt. And now the SysTick interrupt now triggers the scheduler. Why? Because there is already a task waiting in the ready list or ready state, isn't it? That's why scheduler kicks in, and the scheduler now allows the ready state task, that is LED green, to run on the CPU. So now this would have done by the interrupt handler itself. That's possible. I'll show you that in a moment. So the problem here is, you see, even though this green task woke up here, so it was delayed for 462 microseconds to schedule it. Strictly speaking, that's not good, because deliberately the ready state task was not allowed to run. This green task could have allowed to run here itself, so when the ISR exits. That you can achieve by using this field in the from ISR API. This is a common field in all from ISR APIs. What you do now is, let's use this field now. Let's explore this API once again right here. So now let's use this field. I'm going to copy this and I'm going to paste here. So just create one variable, and variable name is higher priority task woken. So make this field is equal to PD false initially. Then send the address of this variable here. Now what happens? This PRTOS API, if it finds that notification enables sending notification, wakes up any higher priority task, then it changes this field to PD true. What this API does is, now it's written here, just read it. X task notify from ISR will set this field to PD true if sending the notification caused a task to unblock, and the unblocked task has a priority higher than the currently running task. So in our case, you see at this position, the higher priority task gets unblocked, which is LED green. So what this API does is, it sets this field to PD true. So now if this field is set to PD true, inside this API, a user task got unblocked and it moved to the ready state, and its priority is higher than the priority of the currently executing task. Now it's in your hand to manually jump to a task which just got unblocked. That means now you have to yield from interrupt handler to that task which just got unblocked inside this API. How to yield from interrupt handler to a task? For that, there is one more macro called port yield from ISR. This is a macro you should use to yield from the ISR. So you just have to mention this variable value, that's it. Now you see here, this actually points to this port and switching ISR, and you actually mentioned PD false or PD true here. If it is PD true, then only contact switch will take place. You see here it calls port yield. So if it is false, then it has no effect. What this macro does, once the ISR exits, this macro makes higher priority task which got unblocked here to resume on the CPU. Let's test this. Now let's see the difference. I'm just going to rebuild and reflash this code. Let me just run this and let me just recapture. So here you see I'm getting the trace, and I'm going to press button a couple of times. Let me pause the recordings and let's see. This is a place where I received the first interrupt, and you see now when the ISR exits, the scheduler comes into picture. The reason for this is this macro. You manually made the scheduler to run so that the scheduler can pick the higher priority task which is there in the ready state, and it schedule it to run on the CPU. Here the idle task was running, and the idle task was interrupted by the interrupt. That's the interrupt handler, and after that the exit of the interrupt handler triggered the scheduler, and scheduler picked the higher priority task to run on the CPU. That's why the idle task didn't resume here. So the green LED task actually resumed and it got deleted here. And after that, the control came back to the idle task like that. Try to get the trace and analyze further. I will see you in the next lecture.